Kenny Kirby, and this is Lab 3, the magnetic field of a bar magnet. For our introduction, or our purpose within the lab, we want to observe and understand the relationship between magnetic fields and distance, and topics of magnetic superposition and B-field visualization are prevalent in this lab. For the experiment itself, the distance dependence and Biot-Savart law leads us to real-world application of the magnetic moment of a bar magnet, and the results within this lab are that the dipole moment is equal to 3.07, and the distance dependence is equal to negative 2.86. For some of the fundamental properties of the lab, we start off with the distance dependence formula of a bar magnet in order to get N, and we have next the magnetic field magnitude of a dipole on an axis, which we'll set equal to each other later on in order to find N and K. And then for the next equation we have the logarithm of both sides of a plot of magnitude of B versus R. This helps us get N as a slope and K as an intercept in order to easily find. And finally, we have the Biot-Savart law itself. We also want to assume that the bar magnet acts like a magnetic dipole, so we can apply a Biot-Savart. For the experiment itself, we start off with determining the location of, or the direction of magnetic north. This will help us in canceling out the magnetic field of the Earth. And then secondly, we'll locate the magnetometer in the phone by moving the phone up and down from both angles pointing north, and mark these locations with tape in order to get the location of the magnetometer within the phone. Moving the phone from different distances will obtain the values B for X, which will equal 20, 70, 120, 170, and 220. And then we'll find the perpendicular distance needed for the phone to create a 45-degree angle with the bar magnet after finding the distance of one side that creates a magnetic magnitude of 100 microteslas. We'll record these different magnetic field components in an Excel spreadsheet. For the observations, I found the various distances where the B of X, or the magnitude of B of X, equaled the values from before, and then I found the distance for the perpendicular side that would take to get to 100 microteslas. I found the effect of the Earth on the Y component of BNet, and then I solved or input the data for the magnitude of BNet overall. For the data and calculation side of things, I ended up solving for mu within the equations given from earlier after I set them equal to each other, and then found the slope from the graph from before, which was negative 2.86, and then solved through the rest of the equation for mu, which was 3.07. Onto the GloScript coding side of things, I created my magnet at the origin and then included the magnitude of the magnetic moment. I created the function for the magnetic field, scaled the arrows so that they fit on the screen, and then was able to create the observation locations that we'll be using later on. I then drew 2 arrows to represent the magnetic field on axis, and then 4 more arrows to represent the magnetic field perpendicular to the axis, which you'll see with those first 2 examples. And then I created the average distance that was perpendicular to the experiment in order to get the value of D, which was how far away the phone was using the perpendicular location. I then created the observation location at 45 degrees from the axis. I drew an arrow to represent the magnetic field 45 degrees from the axis and determined the magnetic field magnitude. Here we have the output from earlier. You can see my result is 3.37 times 10 to the negative 5 for the magnetic field magnitude. And we can reach 2 conclusions with this. When the magnetometer is far away from the magnet, it measures near 0 magnetic field in the x direction. And as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. As well as this, the computed model calculated the magnitude of B at 45 degrees to be 3.37 times 10 to the negative 5, while the experimental model gave 5.56 times 10 to the negative 5. And these values can really be from a lot of different things. One reason that the values may not be the same is because these measurements were taken using the magnetometer in my phone, which may not have been found precisely, and the readings could have all been taken from, or they would have had to all been taken from the correct positioning of the phone in order to fully account for any issues. Some of the what-if questions. If I hadn't oriented your experiment to compensate for the magnetic north, the readings may have displayed incorrect readings since it would also be taking into account the Earth's magnetic field instead of starting with an x component at 0, which would then skew further calculations. And if I were to stick two identical magnets together end to end and run the experiment again, the magnetic field direction would remain the same, but the magnitude could be up to double what it originally was. Thank you.